previous example, we were finding the limit of functions that were defined at the point that we were trying to get the limit at. Now we want to look at limits at boundary points. So these may be boundary points that are not in the domain. So first let's define a couple terms here. Let R be a region in R2, an interior point of R. P will be an interior point if it's possible to find a disk centered at P that contains only points of R. So if P is an interior point, there will be some disk around it where every point in that disk is contained in R. A boundary point, so Q is a boundary point, means that every disk centered at Q will have at least one point that's in R and at least one point that's not in R. So interior or boundary points. Now a region will be open if it consists entirely of interior points. So an example of a set that contains none of its boundary points, I'm talking about sets in the XY plane right now. Let's say we were looking at an open disk. The boundary points of this disk would be the points on the edge of that circle. So this is a circle that's actually contains none of its boundary points. So this region would be an open region because it consists entirely of interior points. Any point you take in here, we can find a disk that's entirely contained inside that region. Now a region's closed if it contains all of its boundary points. Well, an example of a closed set, a closed region would be a circle that contains the edge. So this would be a closed region. And it does contain all of its boundary points. Every boundary point is along the edge and it is contained in that set. Give an example of a set that's neither open nor closed. Well, one example would be something like this. So it has some boundary points down here that are not included in the set. This would be a boundary point not included in the set. But it does contain some of its boundary points. Another example would be an annulus, which would be like a ring with a hole in the middle. So maybe the outside edge is contained in the set, but the inside's not. So this would be a region that would be neither open or closed as well. Okay, I want to identify this graph, and I want to find the limit as xy approaches 4, 4. You can see that if you just tried to evaluate, you would get 0 over 0, which is undefined. So because the limits each exist, the limit of the numerator is 0, the limit of the denominator is 0, but you can't break this up to be the limit of the numerator over the limit of the denominator if the limit of the denominator is 0. That's one of our limit laws. So what we'll do in this case is we'll look at this algebraically. If we want the limit as xy approaches 4, 4, I can rewrite this numerator as x plus y times x minus y. And notice I can now, as long as x is not the same as y, which if xy's are approaching 4, 4, and I'm not coming along this path where y is equal to x, as long as I'm not trying to approach along that line there, then x and y won't be the same. So if assuming x and y are not the same, which of course we can see that the domain of this function is all the points so that x is not equal to y. So you approach 4, 4 from any point in the domain, and this limit would be the same as the limit of just x plus y, because we could cancel those common factors if x and y are different. And now we can easily calculate this limit. This limit would just be 4 plus 4, which would be 8. So now, I want to look at two different paths. Where I'm not approaching 4, 4 along the line y equal to x. So let's look at the domain just as an xy plane. We're trying to approach the point 4, 4. We want to approach this point, which isn't in the domain. And notice the domain is all the points so that x is not y. So the domain is everything except points along this line. Now, this graph will be the same as this plane. Now look at this equation right here. This is z equal to x plus y. That's an equation of a plane. The plane that we see in the graph has a line missing out of it. Now the line missing is corresponding to the points that are in this line y equal to x in the xy plane. So there will not be points in this plane for those values of x and y. Now, looking at approaching 4, 4, somehow the sides along the line y equal to x. Let's approach 4, 4 this way. Now, if I look at points along this path, they have y coordinate of 4, and the x coordinate is approaching 4. So what I'm going to look at is the points x, y approaching 4, 4, but the values y are constant. So that means that I've got x comma 4 approaching 4, 4. Now, if the y value is 4, that's the same thing as the limit of x squared minus 16 over x minus 4. And since the y values are constant, 4 all the time, that means that x is approaching 4. Now recall how we did this back in Calculus 1. This is the same thing as the limit of x plus 4 times x minus 4 over x minus 4, and x is approaching 4. So we've reverted this to a limit with just a single variable. And so we know that limit is just the limit of x plus 4 as x approaches 4, which gives us 8. Now let's find another way to approach the point 4, 4, but we can't do it along the line y equal to x. So let's now approach it this way, vertically. I'm going to come along the vertical line x equals 4. So that limit of this function points on that vertical line will have an x coordinate of 4, but the y value is going to be getting closer and closer to 4. So that will be the limit of 4 comma y is approaching 4, 4. And that means our x is always 4, so we have 16 minus y squared over 4 minus y, which will be the limit. Now notice since the x's are 4s all the time, y is approaching 4. Y is the only variable. So we could rewrite this as 4 plus y times 4 minus y over 4 minus y, which would be the limit of 4 plus y as y approaches 4, which would again just be 8. We've changed it to a limit with just a single variable. Now, trying to graph this function, I want to remind you of a situation back when you were graphing the function y equal to x squared minus 4 over x minus 2. To graph this, you noted that x could not be equal to 2 because 2 is not in the domain of the function. But if x is not 2, this equation is equivalent to x plus 2. That's if x is not 2. So when you were graphing this, this is the graph of y equal x plus 2, which was this line, except x couldn't be 2. So we actually had a hole in the graph here at the point 2, 4. So this equation was just a line with a hole in the graph at 2, 4. And so if you wanted the limit approaching x equal 2, then that limit was going to be 4. And that's exactly the situation we have here. This function is equivalent to the plane z equal x plus y, except it's not defined when x and y are the same, which means it's not defined for this domain y equal to x. So there will be that missing line through that plane. So this graph is very similar to the graph that you did back in Calculus 1, like this. New line. Okay, now let's find one more limit at a boundary point. If you try to evaluate this at the point 4, 1, you'll get the square root of 4 minus 2 times the square root of 1, so you get 2 minus 2 in the denominator. So the domain here is the set of all points x, y, so that the square root of x minus 2 times the square root of y is not 0, which is equivalent to the square root of x not equaling 2 times the square root of y, or x not equaling 4y. So set of all points so that x is not 4y. So the domain consists of all the points in the xy plane except points on that line. And so now if we're approaching the point 4, 1, the domain is the red, or the points not in the domain are in red. So we have to approach 4, 1 ways other than that path along that line, x equal 4y. So now, you don't have to think too hard on this one. Just do it algebraically. The same thing you did in algebra in Calculus 1 is you try to simplify this expression. So can you simplify that? What will help us simplify this will be getting rid of the radicals in the denominator. So we're going to multiply by the conjugate of the denominator over itself. Remember, the conjugate just changes that middle term sign. That's just a little trick to getting rid of radicals sometime. So I'm going to take this function and I'm going to multiply the numerator and the denominator by the square root of x plus 2 times the square root of y over itself. So multiplying out the denominator, and I'm going to go ahead and factor the numerator while I'm going. I'm going to notice there's a y in common with those first two terms, so it's going to be x minus 4y times y, and I'm just going to leave this other thing factored out. I'm not going to multiply the numerator. I will multiply the denominator. In foiling, I get x minus 4y. And notice that that allows me to cancel a term, and that's actually the term that's causing that denominator to be 0. So again, when you have that common factor, all it's doing is it's taking a line out of whatever the graph of that other surface is. So this, canceling these two terms, becomes the limit of y times the square root of x plus 2 times the square root of y. And now evaluating, since I don't have to worry about anything existing anymore, it'll be 1 times the square root of 4 plus 2 times the square root of 1. 1 times 2 plus 2 just gives us 4. So the limit will be 4. That's the z value for this function. This is the function z equal, and that's the function of x and y. The z values will be approaching 4 as the points in the plane are approaching 4, 1. So again, we can't approach along this line because that line is not in the domain, but we can approach from any other angle. We're just coming from any direction to the point 4, 1, and the z values are getting closer and closer to 4. So there will be that limit, so we understand something about the behavior of that surface at the point 4, 1. Even though the point itself does not exist, the z values are near 4.